fourth electron displacement change. It is called a hyperconjugation. 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 Hyperconjugation is the delocalization of carbon hydrogen sigma electrons. Carbon hydrogen sigma electrons along with a conjugated multiple bond, pi bond, sigma bond, along with a carbon-carbon multiple bond, conjugate pi bond, double bond or a triple bond, pi bond. So the delocalization of carbon hydrogen, see remember, carbon hydrogen sigma bond with a conjugated pi bond. Conjugate means alternate pi bond. That's called a hyperconjugation. The displacement of a carbon hydrogen sigma electrons. Two electrons are delocalized. Two electrons are delocalized with a conjugated pi bond, say double bond or a triple bond. Let us take the case of CH3, CH2, CH, it is not a CH2, it is a CH double bond, a CH2. And this compound is propene. That's our propene. CH3, CH double bond, CH2, propene. Propene is found to be more stable. It has got some acidic character also. And it is due to the phenomenon hyperconjugation on the CH3 group. So let me draw the structure of the CH3 fully. Say carbon, sigma bond hydrogen, sigma bond hydrogen, sigma bond hydrogen, and here carbon, sigma bond hydrogen, then double bond carbon, there is sigma bond hydrogen, sigma bond hydrogen. And that is the structure of our propene molecule. Now, you can see that there is a delocalization of the carbon hydrogen sigma electrons with say a conjugated pi bond. Conjugated means alternate. The next one, say sigma bond, then pi bond. This is sigma bond only, it's a pi bond. See here, this carbon hydrogen electron pair is shifted like this. And then the pi electrons will be remaining with the CH2 group. So what will be the new structure formed? Here there is the structure like this. See carbon, sigma bond hydrogen, and electron pair is shifted. So there will be a double bond. Then here there is a hydrogen, sigma bond hydrogen. The pi electron is going to the next carbon atom. So there is only one bond here. So here H2CH2, and since electron is going to this one, there will be a negative charge on the carbon atom. On the carbon atom, there is negative charge. So what happens to the hydrogen atom? From the hydrogen atom, electron is removed. The electron is lost from the hydrogen atom. And so, hydrogen atom remains as H plus ion here. H plus ion. And you see here, there is no actual bond between the hydrogen atom and this carbon, between these two. The first carbon atom with which it had formed a sigma bond. There is no bonding now. Anyhow, this is the structure formed. And this is called the hyperconjugated structure. The new structure formed. That's called a hyperconjugated structure. Here, there is no actual bond. There is no actual bond between carbon and H plus ion here. There is no actual bond between carbon and the hydrogen ion. So the positions are maintained the same. We are maintaining the position the same. Since there is no bond between H plus and the carbon atom, it is called no bond resonance. No bond resonance. It is also known as no bond resonance. It is called a resonance because a pair of electrons between carbon and hydrogen is shifted. So there is a resonance. Still there is no bond between hydrogen and carbon. And therefore, it is called a no bond resonance. This was studied well by Baker and Nathan. And it is called the Baker-Nathan effect. Baker and Nathan effect. Baker-Nathan effect. So hyperconjugation is also known as no bond resonance or Baker-Nathan effect. Baker-Nathan effect. It is called, it was studied by Baker and Nathan, and so it is called the Baker and Nathan effect. It is called a no bond resonance because there is shifting of electron pair, but there is no actual bond between the H plus ion and the carbon atom. So it's called a no bond resonance. The structure will not stop there. It will be having another bond. In the next instance, this electron pair moves to this gap and a new bond is formed between H plus and C. And so the structure will be C. Here there is H. There is a sigma bond H. A double bond CH. And here there is a CH2 minus, and now the H plus, it is here, at the position of H plus. It will not remain there. Say shifting is like this again, and there will be another structure. And it is CH, and here there is H plus, double bond CH, and CH2, there is negative. Okay. It will not stop there. It will go to another shifting. Say it is like this. Electron pair will be shifted to this position, so that this electron pair goes to this position, and you will get to the original structure. The original structure, that is a CH3, all are sigma bonds, and here there is a single bond, here there is a CH, and here there is a double bond, CH2. The original structure is obtained. See, during the course of the change, 3 intermediate structures are formed. See, one here, there is one structure, there is another structure here, and here also another structure. And the intermediate structures are the hyperconjugation structures, hyperconjugated structures. So from one methyl group, CS3 group, from one methyl group, there can be three hyperconjugated structures. More the hyperconjugated structures, more stable the molecule is. From one CH3 group, there can be three hyperconjugated structures. So let us say go back to the hyperconjugation. So what is meant by hyperconjugation? It is the delocalization of carbon hydrogen sigma electrons. Sigma electrons. Carbon hydrogen sigma electrons with a neighboring conjugated pi bond. Alternate. The conjugated the pi bond. That's called the hyperconjugation. It is also known as no bond resonance because there is shifting of electron pair and so it is a resonance, but there is no actual bond between the H plus ion and the carbon atom. And so it's called no bond resonance. Studied by Baker and Nathan, and so it is called the Baker and Nathan effect also. From one methyl group, CH3 group, we get three hyperconjugation structures. From one methyl group, there can be three hyperconjugated structures. So these are the four electron displacement changes we have to study. Okay. Now let us go to, say, a phenomenon that you have studied in the 10th standard. It is called isomerism. Isomerism. In the 10th standard, you have studied only one type of isomerism. We are here to see various types of isomerisms. Okay, let us try to define what's meant by isomerism. You know, the phenomenon in which molecules exist with the same molecular formula, but different arrangements of atoms, different arrangements of atoms and different properties for the molecules, different properties. That phenomenon is called isomerism, and such molecules are called isomers. Such compounds are called isomers. So isomers have same molecular formula, but they have different arrangements of atoms and different properties also. They have different properties. So the phenomenon in which molecules or compounds exist, the same molecular formula, but the different properties and the different arrangements of atoms. That's called isomerism. And such compounds are called isomers. These are different compounds. So the different compounds with the same molecular formula and different properties are known as isomers. Let us see the classification of isomerism. Say, it can be broadly classified into structural isomerism, and second one is called stereo isomerism. Structural isomerism and stereo isomerism. Let us see what's meant by structural isomerism. Here, the isomers have same molecular formula, no doubt, but they have different structures. They have different structures. The molecules or the compounds have different structures. Same molecular formula, but the structures will be different. And that isomerism is called structural isomerism. But in the stereo isomerism, here also the isomers have same molecular formula, but they have different spatial arrangements, different different spatial arrangements of atoms, different spatial arrangements of atoms, different positions in space. In space, the positions will be different. The atoms are arranged at different angles. At different angles, we have to consider the angle, the complete geometry, three-dimensional geometry is to be studied when we deal with the stereoisomerism. So, isomerism can be broadly classified into structural isomerism and stereoisomerism. In the structural isomerism, the isomers have different structures. But in the stereoisomerism, the isomers have different spatial arrangements of atoms, the three-dimensional arrangements. The three-dimensional arrangement of the atoms, spatial arrangements. We have to consider the direction of the bonds. We have to consider the direction of the bonds. Covalent bonds have directional property. Covalent bonds have directional property. So, in the stereoisomerism, we have to consider the direction of the covalent bonds also. The direction of the arrangements of the atoms in space, that must be considered. So, stereoisomers have different spatial arrangements, but structural isomers have different structures only. That is, say, the further classification of structural isomerism can be again classified into four types. One is called the chain isomerism. Chain isomerism. That you studied in the 10th standard. Then, second is called the functional group isomerism. Functional group isomerism, or simply functional isomerism. Then, C, position isomerism. Position isomerism. And D, metamerism. Metamerism. So, structural isomerism is classified into chain isomerism, functional isomerism, position isomerism, and metamerism. While stereoisomerism is classified into geometrical isomerism, and the second is called optical isomerism. Optical isomerism. The only one you have studied in the 10th standard. Now there is the extension of isomerism. You know, isomers are same molecular formula but a different structure you study in the 10th standard. But that is only in the case of chain isomerism. We have to see the other types of isomerisms also. So, isomerism means different compounds with the same molecular formula, but different properties and different arrangements of atoms. Such molecules, such compounds are isomers. Two types of isomerism, structural and stereo. Structural, they have different structures. Stereo, they have different spatial arrangements of atoms. Then, structural, again classified into chain isomerism, functional isomerism, position isomerism, and metamerism. Then stereo isomerism, classified into geometrical isomerism and optical isomerism. Let us see one by one. Let us go to the chain isomerism first. So, what is chain isomerism? Chain isomerism. Okay. Chain isomers have, they are isomers. So these isomers definitely they have the same molecular formula, but they have different carbon skeletons. Do you remember? In the 10th standard, alkanes, different carbon skeletons. So chain isomerism. Isomers have they have different carbon skeletons, carbon chains, different carbon chains or carbon skeletons. There will be different carbon chains or carbon skeletons. And so chain isomerism is also known as skeletal isomerism. It is also known as a skeletal isomerism. Let us take one example. Say a compound with a simple compound with a molecular formula CH, C for H10. C for H10. You may remember the name of this compound. It's an alkane. We have studied this in the tense, and it is our butane. So our butane molecule. C for H10, butane. Let us try to draw the various structures of a C for H10. How can you draw the various structures? It is not to study it by heart. Not simply study it by heart. You make use of your brain. The things you have to remember are this. You draw the possible skeletons using the atoms which have valency more than one. Draw the possible skeletons using the atoms given in the formula. So various atoms with a different, they have valency more than one, valency 2, valency 3, valency 4, etc. That is the first step you have to do. Draw the possible structures with the atoms having valency 2, 3, 4, 5, etc. That is valency more than 1. That is the first step you have to do. Okay, all of you follow Vidur, Krishna, Adul. You follow the mechanism. Now you come to this compound C4H10. C4H10. In C4H10, which are the atoms that have valency more than 1? You think of carbon. Valence of carbon is equal to, Abdul, you know it. That is equal to, valence is equal to 4. But valence of hydrogen is equal to 1. So for the time being, you just leave hydrogen atoms. So you draw the possible skeletons using 4 carbon atoms. All right. So one possible skeleton is this. One, it is a chain of a straight chain of 4 carbon atoms. That is one possible skeleton. All right. Am I right? 4 carbon atoms in a chain. Catenation, carbon-carbon bonds, catenation. Then you think of another skeleton in which 3 carbon atoms in a chain, and the 4th carbon atom is a side chain. All right. The 4th carbon atom is a side chain. We cannot draw any other basic skeletons using 4 carbon atoms. We can draw only 4 basic skeletons. We can draw only these two, only two basic skeletons using 4 carbon atoms. Another thing, when you draw the side chain, A side chain should not be drawn from the terminal carbon atoms. Should not be drawn. The side chain should not be drawn from the end carbon atoms, terminal carbon atoms. But it must be drawn a carbon atom other than the terminal carbon atoms. So here there is only one carbon atom between the terminals. So that is drawn from the middle carbon. Okay. Now we have drawn the basic skeletons. All right. Now you try to complete the structure. The other element, the other atom to be added, that is hydrogen. Because the given molecule is C4H10. All of you are alert. I cannot see you. Say, where are you? Okay. Okay, friends. Are you alive? Are you sleeping? Or you follow this? So you draw a skeleton first. Here we have only Nia, Anthony, Rajas, Emmanuel. All of you, please wake up. It is time to take tea. Come on. The tea is ready. Get up. Home has come. Okay. So you draw a skeleton using all these are the basic points you to remember in organic chemistry. Draw a skeleton, possible skeletons. In the given sample, C4H10, there are 4 carbon atoms. So we can draw only 2 skeletons. Then you complete the structure using hydrogen atoms. So go back to that. Hydrogen atoms are, say how valency of carbon is equal to 4. So we can add 3 more hydrogen atoms to this. Okay. Take the other carbon. 2 bonds, 2 covalent bonds are already formed. So there is provision for only 2 more covalent bonds and 2 more hydrogens. See? Similarly, the other carbon, CH2. Come to the last one. There are 3 more vacancies or 3 more valencies, and you can add 3 more hydrogen. Now you take the number of hydrogen atoms. Take the number of the hydrogen atoms. Does it tally with the given formula? Check whether it is matching with the given formula. What is the total number of hydrogen atoms in the structure drawn?
10.
10.
Is it not? 10.
Yes,
So,
sir.
with the given formula. All right. Similarly, you come to the others. Here, CH3. Organic chemistry is a very simple subject. Please don't make it more complicated. Here, only 1 hydrogen. Here also, 3 hydrogen atoms. You know the technique. Here also, 3 hydrogen atoms. Now you check the number of hydrogen atoms. That is equal to 10. That is in agreement with the given formula. So C4H10, it can represent 2 molecules. 2 molecules. And what is the difference in the molecule, the structure? See here, a straight chain of 4 carbon atoms. But in the second compound, there is Manuel. Get ready. See the difference. Carbon chains are different. Carbon skeletons are different. Okay. And this type of isomerism is called chain isomerism. It is also called skeletal isomerism. It is also known as nuclear isomerism. Various terms given. Nuclear isomerism. Nothing related to the nucleus of the atom. Nothing related to the nucleus of the atom, but related to the carbon skeleton. So, chain isomerism, skeletal isomerism, or nuclear isomerism. The carbon chains are different. The carbon skeletons are different. The carbon nuclei are different. And these two are examples for the chain isomers. These two compounds are chain isomers. One is called a normal butane, the other is called a, so 1, 2, 3, that is isobutane. No, you don't bother about the name now. Leave it there. So okay, here there is a difference in the carbon chain. And these two are examples for the chain isomerism. I have taken only one pair. More details. I shall take one more example. Say C5H12. C5H12. You just try. First you draw the possible structures using 5 carbon atoms. All of you ready? All of you please try. A chain of 5 carbon atoms. Straight chain of 5 carbon atoms. Then a straight chain of 4 carbon atoms. 4 carbon atoms. And the fifth one is side chain. It can be drawn from any one of the middle carbon atoms. Anyone you like. So, okay, for example, from here. If anybody has drawn from the other carbon, don't worry, keep it as such. That is also correct, 100% correct. Okay. So, 4 carbons in a straight chain, fifth one is a side chain. That is the only possibility. If you draw on the other carbon, the same thing. No difference, a repetition. Now, a third possibility. 3 carbon atoms in a chain. And 2 are side chains. 2 side chains. 1 carbon here and 1 carbon here. 2 side chains. Okay. Now you try to complete the structure. Shall I draw the structure directly? Complete it. How many hydrogen atoms will be there on this carbon? Vidor?
3.
How many hydrogens?
3.
3, correct. Why do you hesitate, man? Whenever I ask me a question, you give the answer. It may be right or wrong, it doesn't matter. There is nobody else to hear. Only we are here. I also commit mistake a number of times. So there is nothing to worry. Okay. You come to the second, CH2. Anthony, what about another carbon? This one? How many hydrogen atoms are possible? Anthony? Anthony is not there. He has gone to Pullada. Okay, CH2. This is a CH2 and a CH3. Okay. Come to this. CH3. Here. H2. C. How many hydrogens? Oh, valence carbon is equal to 4.
Sir, 1.
How many hydrogens are possible?
1.
1. Yes. Why do you fear? This one, CH3. This is a CH2. This is a CH3. Okay. Even this is CH3, 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 CH3. Now, how many hydrogen atoms are there on the middle carbon? Achyut?
No, sir.
I did not hear.
No hydrogen.
No hydrogen. Because all the 4 valences are used. Now, let me ask you a question. Say, what is the nature of the middle carbon? Is it primary, secondary, or tertiary? I stopped at tertiary very purposefully.
Quaternary.
Achut will say, Achut say, primary, secondary, or tertiary, or anything else. Punya, somebody told it already, not to you. Achut, what is primary? Direct linkage to only one other carbon. Okay. What is secondary? Direct linkage with 2 other carbons.
2 carbons.
Tertiary? Direct linkage with 3 other carbons. Now what about this? Come
4
on,
carbons.
a bit louder.
4 carbons.
Carbon, so it is. Come on. So much is correct. And what is his name? Punya, please help. What is it? Quaternary. This is a quaternary carbon. Okay. Quaternary carbon. So I will ask such a simple questions, say during the course. That is to make you thorough, that's all. Eh? That is not to show that you don't know anything, not that. That is to make you thorough with the subject. That's all. So these three are the names we can study afterwards. So these three are the chain isomers. Okay. Now let us go to the functional isomerism or a functional group isomerism. Functional isomerism or a functional group isomerism. Yeah, okay. Functional group isomerism or a functional isomerism. See here, same molecular formula, but different functional groups. The isomers have different functional groups. Different functional groups. For that, we had studied functional groups. It was not for a joke. It was not to waste time. Say, we are going in a sequence. There is an order. Say, I have arranged everything in an order. Different functional groups. That is a heteroatom or groups of atoms that confers specific properties to a class of compounds or to a compound. The group that functions in chemical reactions, that's called a functional group. So here, functional isomers or functional isomerism, they have different functional groups. Same molecular formula, no doubt. Let us take C2H6, C2H6O. You take this molecular formula. Now, how many structures can be drawn? What is the first step? What is the first step? Find out the atoms with the valency more than 1. So which are the atoms here? Come on.
Carbon and oxygen.
Carbon? Two carbons. Only two carbons?
And oxygen.
Oxygen. Yes, correct. There you are. Correct. Oxygen valence is equal to 2. So you try to draw the various possible structures with the 2 carbon and 1 oxygen. You try? You check it. You try. Okay. I shall help. Say 2 carbon atoms in a chain like this. And the oxygen atom at the one end. Can be drawn like this? No. That is one possibility. We know the valence of carbon is equal to 2. So, oxygen is equal to 2. So, oxygen can form 2 covalent bonds. Atul, have you got any other idea? Have you got any other structure? Atul?
No, sir.
You did say oxygen can form valency 2. So you can place oxygen
In the
between.
middle of the
Center.
carbon.
That is also a possibility. You think of the various possibilities. Let your brain work. There is sufficient. There is sufficient. You are gifted with a sufficient intelligence and brain. You make use of it. That's all. You do exercise with your brain. Okay. So, say oxygen atom is between 2 carbon atoms. Because oxygen can form 2 covalent bonds. So these are the 2 basis skeletons possible. Alright? Okay. Complete the structure. Say 1 hydrogen, here 1 hydrogen, here 1 hydrogen. Alright? Krishna, you are there? Krishna, He has gone to Guruvayur. Here H, here also H. Okay. What about oxygen now? You know, valence of oxygen is equal to 2. It can form two covalent bonds. Only one bond is formed now. So it can form one more bond with the hydrogen, say like this. Okay. Now you count the number of hydrogen atoms. The number of hydrogen atoms, does it tally with the given formula?
Yes, sir.
Similarly, you come to the other one, CH3, oxygen. How many hydrogen atoms will be there on oxygen atom? Atul can say.
No. No hydrogen.
Atoms can be there. Normally, on in this structure,
No hydrogen, sir.
hydrogen, because only two valency, covalence is equal to 2. 2 are already formed, there is no provision. So there is hydrogen here. C2H6O. Okay. Those structures we have drawn. Now you think of the functional groups. See, different functional groups. Here the functional group is OH, alcohol. Here the functional group is O, that is ether. This compound is alcohol, and this compound is ether. The functional groups are different. Functional groups are different. See the structure of an ether. In an ether, there is an oxide linkage between two carbon atoms. In an ether, there is oxide linkage between two carbon atoms. Okay. So here the functional groups are different, and therefore this is an example for functional isomerism. We have to see the others. You can see in the coming classes. Stop now.